When a multi-agent system collapses, the final error message generated in the console rarely points to the origin of the problem. That terminal log is almost always a downstream symptom of a much earlier mistake. If a long-horizon agent executes dozens of actions and finally throws an exception on step 47, working backward from that last message is an operational trap. The final output obscures the sequence of events that actually derailed the task. Modern autonomous architectures create a massive observability gap. Because their behavior is multi-step and stochastic, every execution generates a unique trace, making it exceedingly difficult to track when and where an agent first drifted off course. The true objective in trace debugging is locating the critical failure step. This is the exact earliest unrecoverable error that doomed the entire sequence, the single point where correcting the action would have changed the outcome. Fixing autonomous systems requires us to audit the specific moment a trajectory breached its operational boundaries, rather than guessing at causes by sifting through the final wreckage. In production, specialized agents operate in open-ended environments. An orchestrator must pass context, instructions, and tool outputs asynchronously to distinct subagents to solve complex queries. Because large language models are non-deterministic, rerunning the exact same prompt will often yield completely different execution paths. A silent hallucination or an invalid argument generated by one agent can easily be passed downstream to another. This mutates the shared context, allowing the system to run on corrupted data for several steps before a fatal crash forces the process to stop. The Microsoft research framework AgentRx introduces a methodology to eliminate this guesswork. It forces unpredictable multi-agent traces through a deterministic validation pipeline. By treating an agent run exactly like an auditable flight data recorder, developers can replay traces step by step against strict known bounds to isolate the exact moment of failure. The first phase of this pipeline targets the logs themselves. Because different benchmark domains and frameworks output distinct event types, AgentRx normalizes these heterogeneous traces into a single, shared intermediate representation. With a unified format, the system can apply universal rules. These begin with global constraints, the static, unyielding laws of physics for that specific agent domain. Global constraints are derived directly from the application's JSON tool schemas and explicit policy documents. If a policy dictates that an agent must verify user permission before executing a write command, that invariant applies to every single trajectory. Static rules alone are insufficient. The pipeline generates dynamic constraints, evaluated locally on the sly using data the agent just processed. For instance, if a search returns 5 items, a dynamic constraint ensures the agent's reported integer matches that array size. Generating these constraints step by step prevents the hallucination caused by asking an LLM to predict all constraints in one pass. Evaluating dozens of rules on every single action would overwhelm the system. To solve this, AgentRx uses guarded triggers. A constraint is bypassed entirely unless the current state matches its specific trigger condition, like a corresponding step index, a required tool name, or an active agent role. When a trigger activates, evaluation routes down one of 2 paths. First, a Python check executes code to validate programmatic bounds, like strict schema matching. Alternatively, a natural language check evaluates semantic policy rules against the current step. The output is a step-indexed validation log recording condition outcomes. Crucially, this links every violation to localized evidence within that specific trace window. This guarded execution process forces a chaotic, unstructured multi-agent trace into an auditable matrix of deterministic evidence. With the evidence secured, the final step involves handing the detailed validation log to an LLM judge for conclusive root cause attribution. Feeding a raw, unparsed trace to an LLM judge and asking it to guess why the system failed yields poor accuracy. The model will frequently hallucinate connections or drift toward downstream symptoms. To prevent this, AgentRx enforces a cross-domain 9-category taxonomy, providing a standardized diagnostic language. For example, invalid invocation is a definitive bucket for structural failures like missing arguments. Alternatively, if an agent hits a CAPTCHA, the judge categorizes the failure under guardrails triggered, as execution was blocked by external controls. The judge operates under a strict instruction. It must scan the evidence logs sequentially from start to finish to locate the very first unresolved violation. The term unresolved is necessary. Autonomous agents frequently malform a tool call, recognize the API rejection, and successfully correct their syntax on the immediate next step. Constraining an LLM judge to attribute tightly localized evidence against a rigid taxonomy removes the subjectivity from postmortems, yielding repeatable root cause identification. Microsoft researchers ran this framework against 115 complex trajectories across structured APIs, incident response workflows, and open-ended web environments. There is a prevailing industry assumption that long-horizon agents fail primarily due to poor planning capabilities, hallucination, or a fundamental misunderstanding of the user's intent. This chart compares the frequency of different critical failure categories across benchmark domains. The single most frequent critical failure is misinterpretation of tool output, causing over a third of all unrecoverable errors in generalist environments. Operationally, this means the agent successfully constructs a plan, invokes the correct tool, and retrieves the exact right data, but then reads it incorrectly, like miscounting the available product variants in a return JSON array. This single misread triggers a collapse. The data shows an average failed trajectory contains multiple cascading errors, with 68% of runs suffering at least 2 distinct failures before halting. This data points to a clear engineering mandate. The highest leverage improvement you can make right now is not writing clever prompts for smarter reasoning. It is implementing rigorous, cross-checkable telemetry and ID provenance for your tool outputs. Building reliable autonomous systems requires developers to abandon the practice of staring at terminal error logs to deduce system behavior. Production architecture must evolve to synthesize tool schemas into rules, execute guarded logic checks on the fly, and produce auditable validation logs that map every single action. Adopting this black box methodology turns the persistent question of why did my agent fail from a forensic art into evidence-backed science. What logging frameworks are you currently using to untangle complex multi-agent traces? Let us know in the comments below. Subscribe to the channel as we continue to break down the architectures required to build scalable, observable, and deterministic enterprise AI.